So in this video, called Starlight, Starbright, we're going to refer to chapter 13 of your textbook and look at luminosity and brightness of stars. So what's the difference between a star's luminosity and its brightness? First of all, we have to look exactly what a star is. It's a huge mass of gas with a core temperature high enough to initiate nuclear fusion reactions, resulting in the radiation of energy. So during these reactions, hydrogen will fuse to form helium and gamma radiation will be given off, along with a huge amount of heat and light energy. Here's a picture of our own star. And here's our galaxy. So our galaxy, the Milky Way, contains approximately 100 billion stars. It's not the largest of the galaxies. The largest known galaxy contains 400 billion stars. So let's have a look at how we classify stars. First of all, we look at their luminosity, the total energy radiated by an object per second. This, of course, will depend on the radius and the surface temperature. Our own sun's luminosity is 3.83 times 10 to the 26 watts. Brightness is the intensity of the light as seen some distance away from the radiant object. It's the energy received per square metre, and it depends on luminosity and, if we're standing on planet Earth, the distance from the Earth. Here's some stars close to the Earth. We've got Procyon, Betelgeuse, Rigel and Sirius. Procyon and Betelgeuse appear the same brightness, but Betelgeuse is much more luminous as it is much further away. We can see that it's 427 light years as opposed to Procyon's 11.41 light years. The distance causes an apparent dimming. Let's have a look in more detail at luminosity and brightness. Here's our old friend, the inverse square law. Brightness depends upon two things, luminosity and 1 over the distance squared from the star. Consider streetlights. They look different in brightness due to the different distances. So next time you're out walking down the street in the dark, look at more distant streetlights as opposed to the ones closer to you. Their luminosity is exactly the same. However, their brightnesses will be different because of how far away you are from them. Let's revisit the inverse square law. Let's imagine our star is surrounded by a sphere and we're looking at the centre of that star. The star gives off radiant energy in all directions, and the sum of all radiation given off in 1 second is the luminosity. The radiation spreads out uniformly and penetrates the whole surface of the sphere. The brightness will be the luminosity divided by the surface area of the sphere, and since the surface area of a sphere is 4 pi r squared, then brightness equals luminosity divided by 4 pi r squared. The relationship, therefore, brightness varies with 1 over the radius squared, or is proportional to 1 over the radius squared. So that means if the distance r were to double, then the brightness would reduce to 1/4 of its previous value, as shown in the equation below. So let's have a look at question 1 on page 12 of your notes. A detector measures the intensity of light from a source as I when placed d meters from the source. If the detector is moved to a distance of 3d from the source, what is the new brightness? Well, we need to apply the inverse square law. So using the inverse square law, it will be equivalent to I times 1/9 of its original luminosity. That's the inverse of the distance squared. As it's 3 squared, it now becomes 1/9 of its original luminosity. Question 2, page 13 in your notes. Use the data provided to show that Procyon and Betelgeuse have almost the same brightness. In the picture below, we can see the data that we need to use. Luminosity is 7 for Procyon and for Betelgeuse 10,000. And the distance for Procyon 11.41 light years and for Betelgeuse 427 light years. However, we need to do something to those units before we can use them. Let's have a look at how this works out for both stars. Okay, if we take the brightness of Procyon, it's its luminosity divided by 4 pi r squared, and this is shown in this calculation here, which has given us 0.004 watts per square light year. We can convert it into SI units by converting our light years into meters, and this is done here. If we now look at the brightness of Betelgeuse, we take its luminosity divided by 4 pi r squared for Betelgeuse and substitute that in, and we get exactly the same value for our brightness for Betelgeuse as we do for Procyon, because of the much further distance that Betelgeuse is from Earth. Let's have a look at question 3 on page 13. How would the brightness of Procyon change if its distance were 3 times its current value? That is, if it were at a distance of 34.23 light years. Well, we take the old brightness and we now divide it by the new distance squared. So we take 0.004 divided by 9, which gives us approximately 0.00044 watts per square light year. Let's check this calculation using the brightness expression, which is the luminosity divided by 4 pi r squared. Well, we simply substitute in the new distance into the old equation, and we get approximately the same answer as we do up here. The difference between the answers is just due to a rounding off error and is minimal. Let's now have a look at temperature and colour, and this is chapter 13.2 in your textbook. We want to look at black body radiation. So a black body absorbs all radiation falling on it. Therefore it's reflecting nothing, and that's the reason it looks black. It's absorbing all light. When it becomes hotter than its surrounding, it starts to radiate electromagnetic energy of its own, and this is known as black body radiation. Radiation is distributed continuously but not evenly across various wavelengths of the EM spectrum. This depends upon the temperature of the black body. So let's have a look at a graph that shows that. Each curve is specific to a particular temperature. Each peak intensity corresponds to a particular wavelength, and the graph clearly indicates there is a direct correlation between the temperature of the black body and the dominant wavelength of the radiation emitted from it. As temperature increases, the wavelength decreases. Now we're going to have a look at Vienne's law. Yes, I know it looks like wine, but it was German, so it's Vienne. This is the relationship between temperature and dominant wavelength emitted by a black body. Wavelength of the maximum emission is related to the absolute temperature of the surface of the black body. And we can see that here, lambda max temperature equals the constant W. So that's the wavelength of the maximum output or dominant wavelength in meters, and T is the temperature in Kelvin, and W is a constant 2.9 times 10 to the minus 3 meters Kelvin, as it is a product of wavelength and temperature. So let's have a look at a black body as opposed to a star. Although a black body is a hypothetical concept, a star's radiation output closely matches the theoretical black body radiation curves. The surface temperature of stars can be estimated by observing their colour. So a cooler star in the 3 to 4,000 Kelvin range produces most of its visible radiation towards the red end of the spectrum and therefore appears red. As the temperature increases, the wavelength peaks in the yellow region and the star will appear yellow. At slightly higher temperatures, the distribution of the radiation is more even and the star will appear white. And a hotter star at about 8,000 K will produce most of its visible radiation at the shorter wavelength end and will appear blue. So bluer stars are hotter than redder stars. And this seems to go against what we normally think about the temperature of objects. But if we think about a Bunsen burner flame, we know that the hottest part of the Bunsen burner is in the blue part of the cone or corona. So what conclusions can we draw? Let's have a look at this photograph showing some stars that we examined before: Procyon, Betelgeuse, Rigel and Sirius. Betelgeuse, shown on the right, is red, so it is the coolest. Procyon is glowing white, so it's slightly warmer than Betelgeuse, but is not the warmest star on this photograph. Sirius and Rigel are blue-white, and therefore they are the warmest stars that we can see here. So that ends our chapter on starlight, star bright. In the next video we'll be examining the Hertzsprung-Russell diagram and how it applies to stars.